In this video, we're going to look at conditional probability and intersections of events. When we compute the probability of event F, assuming that the event E has already occurred, we call this the conditional probability of F given E. We denote this probability as P of F vertical bar E, which is read the probability of F given E. So we're going to read this notation as the probability of F given E. That vertical bar there is read given. So we have the probability of F given E. Example 1. Suppose two cards are drawn from a standard 52-card deck without replacement. What is the probability that the second card is a face card if the first card is a face card? So in this example, we're not just drawing one card from the deck of 52 cards, we're drawing out two cards. And the question is about the second card. So our question is, what is the probability that the second card is a face card if the first card is a faced card? So if I write that using our notation, that's going to be the probability that the second card is a face card given that the first card is a face card. So that's the probability that we're looking for. Well, if we think about our 52-card deck, we know that there are 52 cards and 12 of those cards are face cards. So if the first card that we draw out is a face card, then that means there'll only be 11 face cards in the deck for the second card to be. And there'll only be 51 cards left that we could pick from for the second card. So the probability that the second card is going to be a face card, given that the first card is a face card, is going to be 11 out of 51. Again, the 11's coming from the fact that there will only be 11 face cards left in the deck if the first card's a face card. The 51 is coming from the fact that there will only be 51 cards left in the deck if we've drawn a card. Question B, similar question. What's the probability the second card is going to be a face card if the first card is not a face card? So again, using our notation, what's the probability the second card is a face card given that the first card is not a face card? Well, if the first card's not a face card, then all 12 face cards will be left in the deck for the second card to be. But there'll still only be 51 cards in the deck because we've drawn one card. So the probability that the second card's going to be a face card if the first card's not a face card is going to be 12 out of 51. So again, the 12's coming from the fact that there'll still be 12 face cards in the deck. The 51's coming from the fact that there'll only be 51 cards in the deck for the second card to be. Now 12 over 51 will simplify. We can reduce that. 12 and 51 can both be divided by 3. 12 divided by 3 would be 4. 51 divided by 3 is 17. So we could simplify that to 4/17. And as usual, if we wanted to write our probabilities as decimals, I can bring in my calculator. 11 divided by 51, that would be approximately 0.216. So this probability would be about 0.216. Whereas if I take 12 divided by 51 or 4 divided by 17, either way I get about 0.235. So this would be 0.235. So this leads to our rule. We call this the special rule for computing the probability of f given E by counting. So if E and F are events in a sample space with equally likely outcomes, then the probability of f given E is equal to the number of ways that E and F can both occur divided by the number of ways that E can occur. So again, this is our rule for computing the probability of f given E by counting, and that's what we really used here in example 1. Let's take a look at example 2. Example 2. The General Social Survey asks questions about health and happiness. The table below provides the results. Assume the results are representative of all U.S. adults. So we're given information here. In the rows we have level of happiness. In the columns we have the level of health. If a U.S. adult is selected randomly, what is the probability that A, the person is in excellent health given the person's very happy? So this is a conditional probability. We're given the person's very happy, and we want to know then what's the probability the person is in excellent health. So we're looking for the probability of excellent health given that they're very happy. So in this case, excellent is like F and very happy is like E. So we need to find the number of individuals who are both in excellent health and very happy and divide that by the number of individuals who are very happy. So if we take a look at our table, well, the fact that we're given they're very happy means we're only interested in the individuals in this row. And of the individuals in this row, 5,095 are in excellent health. So we have 5,095 individuals who are both very happy and in excellent health, and we have 11,347 who are very happy. So our probability is going to be 5,095 out of the 11,347. Again, that's coming from the fact that we know they're very happy, so we're only interested in these 11,347 individuals that are very happy, and of those, 5,095 are in excellent health. Now that's a nasty fraction, so we want to change that to a decimal. 5,095 divided by 11,347, well, that is approximately 0.449. So 0.449 is our probability. The probability that an individual is in excellent health, given that they're very happy, is 0.449. Question B. We want to know the probability that the person is very happy, given that the person's in excellent health. Well, how is that different from the question in Part A? Well, in Part A, we're given that the person's very happy. In Part B, we're given that the person's in excellent health. So we have a different given. In Question A, we were looking for the probability they're in excellent health. In Question B, we're looking for the probability they're very happy. So in this case, we're looking for the probability of being very happy given that they're in excellent health. So the difference again is what's F and what's E. In this case, the F is the very happy and the E is the excellent health. So the fact that we know the individuals in excellent health means we're only looking at the individuals in this column, the column for excellent health. And there are 11,022 individuals in excellent health, and of those, 5,095 are very happy. So 5,095 are both in excellent health and very happy out of the 11,022. So 5,095 divided by 11,022. So again, that's a nasty fraction. We want to put that in decimal form. So 5,095 divided by 11,022. So that is 0.462 if we round to 3 places. So 0.462. So if we know the individual is in excellent health, the probability that they're very happy is 0.462. Let's take a look at part C. Part C, we want to know what's the probability the person is pretty happy given that the person's in fair health. So probability of pretty happy given that they're in fair health. So we're given that they're in fair health, which means we're only interested in the individuals in that category. So there are 6,585 individuals who are in fair health. So that's going to be our denominator, 6,585. Now of those individuals, 3,817 are pretty happy. So there are 3,817 individuals who are both in fair health and pretty happy out of the 6,585 individuals that are in fair health. So our numerator is 3,817. Again, that's a nasty fraction, so we're going to put that in decimal form. 3,817 divided by 6,585. So that is approximately 0.580 if we round to 3 places. So 0.580 is our probability. 0.580. Question D. We want to know the probability the person is in poor health given the person is not unhappy. Now this one's a little trickier because we're given a complement. We're not unhappy. So if we look up here in our data, there's 4,443 individuals who are unhappy, but we want not that. We want them to not be unhappy. So we need to figure out how many individuals are not unhappy, and then of that, how many of those individuals are in poor health. So we're looking for the probability of poor health given that they're not unhappy. Again, it's tricky because it's not unhappy. Well, how many individuals are not unhappy? Well, we can figure that out a couple of different ways. One, we know there's a total of 35,394 individuals. 4,443 of them are unhappy, so we could take the 35,394 minus the 4,443 to get the number of individuals that are not unhappy. So that's one way we could do this. 35,394 minus 4,443. That would be the number of individuals who are not unhappy. Now we could also find that by adding the 19,604 and the 11,347. So if we added those two numbers together, that should give us the same result that we have here. Let's go ahead and figure out what that is. So if I take 35,394 minus 4,443, that is 30,951. So there are 30,951 individuals who are not unhappy. Now, of those not unhappy individuals, we got to figure out how many individuals are in poor health. Well, there are 696 individuals who are unhappy and in poor health out of the 1,996 individuals who are in poor health. So we can do the same kind of thing here. I can take the 1,996, that's the total number of individuals in poor health, and subtract off the 696 individuals who are unhappy. And if I do that, 1,996 minus 696, that is 1,300. So there are 1,300 individuals who are in both poor health and not unhappy out of the 30,951 individuals who are not unhappy. Now again, this 1,300 we could have also found by adding the 950 and the 350. So that's a second option for us. Now that is again a nasty fraction. So if I take 1,300 and divide by 30,951, that is approximately 0.042 if I round to 3 places. So 0.042. So if I know the individual's not unhappy, then there is a 0.042 probability that the individual is in poor health. So that concludes example 2, where we'll conclude this video. We'll pick up in the next video.